In this video, we're going to cover 2.1, which is the beginning of Chapter 2 on limits. Limit is essential to the study of calculus. And in 2.1, before we go into study of limits, we will study two problems that limit can resolve that lead us to find solutions of other problems such as engineering physics, a lot of economic problems, and even space travel as documented in the opening chapter of Chapter 2. So the two key problems that lead to the initial formulation of calculus are tangent line problems or instantaneous rate of change, and also area under the curves. So these are the two problems that calculus works on that use the concept of limits, and this section talks about how we need limits to solve those problems. So in the beginning, we'll look at what tangent line problem is about. What is a tangent line? Tangent line is a line that touch at a point. Is the line that would touch the function, a graph at only one point. Okay, so of course it would touch. Is the line that was supposed to touch the graph like that, just tangent to it. If you extend it, of course, it might touch the graph in another point, but we are interested in a line that would touch it only at that point. Now, to get the slope of this tangent line, we need 2 points, right? But we only touch the graph at 1 point. How do we do that? So we would use the concept of secant line that we have learned in pre-calculus. So we define the point A and f of A as the point that you want to have a tangent line on, and then the other point that we temporarily put on the line, x and f of x, so that we have 2 points. And then slope of a secant line would be f of x minus f of a over x minus a. Change of slope is always change of y over change of x. And we call it average rate of change. Average rate of change. And remember, this is the slope only. Okay. If you have the slope and a point, you can find the equation of the tangent line. But eventually, we want a tangent line. So how do calculus approach this? They would just have x approach closer and closer to a, but not equal to a. Because if you're equal to a, then you're dividing by 0. So what happened is they would look at what happened when x is getting closer and closer to a, so that eventually you would have a slope that is called f prime of a, does not use the formula of f of x minus f of a anymore. You use another notation called f prime of a, which is the derivative of f at a point a. Okay, and for rate of change, we no longer call it average rate of change as in secant line. It's called rate of change in secant line, but we call it instantaneous rate of change. At that moment, if x change a little bit, what will y change? So let's do an example to investigate if this is possible. Can we move a point away from a point that you have chosen, point x equal to a, to find the tangent line slope, to find a tangent line slope? So let's look at this function f of x equal to x squared plus 2x minus 1. And we want to find, from a pre-calculus point of view, find a secant line from x equal to 1 with another point that is 1.5. 3 over 2 is 1.5 away from 1. And we want to find the slope of that line. So the slope would be equal to y2. So this is y2, y1, right? 17 over 4 minus 2 over x2 minus x1. 3 over 2 minus 1. So fraction, just change 2 to 8 over 4. Fraction, subtraction, 3 over 2 minus 2 over 2. So that would equal to 17 minus 8 is 9 over 4 over 1 over 2. Multiply by 4, top and bottom, will give us 9 over 2. So 4.5, right? But this is only a secant line slope. It's not exactly the tangent line slope. What happens is if I move the point closer and closer, so let's, instead of doing 1.5, I do 1.25, right? So the slope would be, the secant line slope would be equal to 49 over 16. Okay, this is f of 5 over 4. So minus 2 over 5 over 4 minus 1. Again, use fraction subtraction. 49 16 minus 32 over 16 divided by 5 over 4 minus 4 over 4. You just have to do a lot of this fraction. So it's 17 over 16 over 1 over 4. Again, multiply top and bottom by 16. It would become 17 over 4 is 4.25. As a matter of fact, we can actually do this on a decimal. So if you look at decimal, I have decimal started here. X squared plus 2x minus 1, that's the function that we have. And if I do f of, what was it, 5 over 4, right? This is the y, minus f of 1, right? And then have it divided by 5 over 4 minus 1. You can see that it's 4.25. So decimal is a graphing calculator, but actually is a calculator also. So 4.25. So we see that it is getting closer to 4.2. Could it be 4.2? Could it be 4.1? We really don't know. So let's choose a point that is really close to x equal to 1. So maybe we'll choose one that is 1.01 and f of 1.01. 1 comma 2, right? So like this. So you will use one that is really, really close. So slope of, and again, would equal to, let's use decimal now because these are a little harder. So instead of 5 over 4, I would say 1.01 minus f of 1, and then the bottom would be 1.01 minus 1. Oh, it's 4.01, right? The answer is over there. So we would use decimal is 4.01. So you can see that it's from 4.5 getting closer, 4.2, 4.01. At the limit, so at the limit, if you believe, then the tangent line slope of the tangent line that only touch at one point, not even 1.01, would equal to 4. And we also say the instantaneous rate of change is equal to 4, or f prime of 1 is equal to 4. At that point, the tangent line slope is 4. So that's how we think that it would happen. You have to trust that it would get closer to 4, but not exactly 4. So the application is if the function is describing distance, the instantaneous rate of change would be instantaneous velocity. The average rate of change would correspond to average velocity. So in application, we would use a distance function to estimate instantaneous velocity, kind of like when you drive a car, the speedometer tells you instantly what your velocity is. Okay, so we already studied some movement function that is free falling objects. So if you have an object that's free falling from a height of 64 feet, you have something that fall down, free falling. The height from the ground can be modeled by negative 16t squared plus 64 in feet, and t is in second. So we want to estimate the instantaneous velocity at 0.5 second after the object fall for half a second. What is the instantaneous velocity? So again, we would kind of use the analogy with the tangent line. We would use a average velocity at v of average at say 0.49 to 0.5. So just b 4.5 at time of 0.49, what is the average distance over the average velocity? So we would just use decimal again. So instead of f of t, I'll change it to f of t equal to negative 16t squared plus 64, right? And instead of f, now I do s of 0.49. Okay, so this is A. A is at the back, 0.5. At 0.5 second, oh no, this is not F, it's S, right? And then I would say 0.49 minus 0.5. This is the average time, average distance. It's negative 15.84. So from decimal, you go negative 15.84 feet per second. Feet per second. It would every second it fall that much. But I want to know what happened if it fall just 0.01 second further than 0.5. So if I want to find the average velocity from 0.01 second away, 51.51 from 0.5, oh, I got negative 16.16. So you see they are actually close to each other. If you are 0.1 second before and 0.1 second after, negative 0.16 feet per second. So you can see they are approaching a number. What do you think it would be? They are approaching 16 feet per second. Estimate. So we can say we estimate the instantaneous velocity at 0.5 second would be 16. Because just before it is negative 15, just after it is negative 16.16. The second problem is area under curve. So if a lot of applications in economics as well as statistics involve the calculation of area under a curve. And then we can't really do it, but we can cut it into small rectangles with thin rectangles and add the area of the rectangle together. And it turns out if we add all these small rectangles together, the total sum would approaches the real area. So let's try to do one example. Estimate the area of under f of x 2x squared plus 1. So we'll graph 2x squared plus 1 is a parabola, right, up 1. So this is 1 here. And then we wanted to find the area from 0 to 4. Okay, 0 to 4. 1, 2, 3, 4. Like that. So these are not rectangle, but we will pretend that they are. So this one, 1, 2, 3, 4. We use the right hand height as the height of the rectangle. So the first rectangle, let's see how I'm going to use this also to help us. So my f of x would equal to 2x squared plus 1. I want to know f of 1 because that's the height of the first rectangle. It's 3. Or actually, if I wanted that much, I can build a table. Okay, so I would say 1, 2, 3, 4. Okay, so 3, the first height is 3. So if you put down, you would see all those heights. 9, 19, and 33. So I would say this one, because this the space, the width is 1, so this is 3. This is what, 19? Is it? 9 and then 19. 9, because this is 19, 9 height, and this is 19, and this is 33, because this is 1. So the area is equal to 3 plus 9 plus 19 plus 33. You add them together. 3 plus 9 is 54. So the area under the curve is 54. And we would say the real area is, if I have the rectangle thinner and thinner, the real area would be closer and closer to 54. So we can say it is approximately 54. The real area will be approximately 54. And if we cut the triangle thinner and thinner, more and more, not just 4, it would be equal to the real area.